Hello, my name is Steven, and I'm here at the Geek Group to talk to you about what we can learn about adaptations, characteristics that help organisms survive in their environment, from fossils, the traces that those organisms leave behind after they're dead, millions of years after they're dead. We're not going to use real fossils to do this. Instead, we're going to use models, because fossil bones tend to be big and expensive and heavy and fragile. Now, if you've been to a museum with a gift shop, you probably saw something like this. This is a little model Tyrannosaurus skeleton, or at least it's supposed to be. It's about 100 years out of date, and it's not accurate enough anymore, and it was never large enough to be detailed enough to learn very much about it as far as adaptations go, which is why we made you a bigger one. While we can observe organisms adapting to their environment in the laboratory and through careful observation in the wild, those tend to be minor changes. For the big changes, though, to see animals becoming shaped the way that they are today, you have to look at the fossil record. You have to look at what animals looked like in the past. If we know how an adaptation helps a living organism survive, we can suppose how a similar adaptation might have helped a fossil organism survive. For past ecosystems, we can look at modern ecosystems that we think would offer similar habitats, even though they might be a lot smaller or a lot bigger, or be in a completely different part of the world, because environments change over time. We can look for modern creatures that fill certain roles in their habitats, and then we think about how those adaptations might compare to a fossil organism's adaptations. We can also look at the living relatives of fossil organisms. For dinosaurs, we look at modern dinosaurs, which is birds. We also look at their close cousins, which are the crocodiles. This works the other way around too. Fossils can help us understand why modern organisms have the traits that they do. Today, though, we're only looking at one animal. We're looking at Tyrannosaurus Rex. We have a complete skeleton here, but we almost never get a complete skeleton. Usually we only get a few teeth. As it happens with Tyrannosaurus, we're really lucky. We have specimens of Tyrannosaurus that are nearly complete, so we have a really good picture of what this guy looked like. When someone's working on only one part of an animal, they might ask questions and reach conclusions that they need to reconsider when they see the whole thing together. This is how science works. You always need to be open to the idea that new information is going to call everything you previously assumed into question. This happens every day in paleontology. The skeleton you guys are putting together is actually not full-sized. It is 1/3 scale, because an actual adult Tyrannosaurus was huge. An actual adult Tyrannosaurus would be 40 feet long and 13 feet high, which is the size of a semi-trailer. That's big enough that a 4th grader could sit in its mouth. Not that that would be a good idea. Now, size by itself is an adaptation. It weighed about 6 to 10 tons, which is completely different from anything that's living today. We don't have two-legged animals that big walking around. Remember, environments change, and organisms either adapt, move away, or die out. For one thing, an animal this big would need a lot of food available. It would need to be taking in a lot of energy from its environment. Scientists actually figured this out. They figure it would need about 37 pounds of meat a day, which is 40,000 calories, which is a human every 3 days or so, or 15 large one-topping pizzas. So how do we know that? Well, we can actually test hypotheses about extinct animals. We can look at its energy needs by examining its bones. You guys have probably looked at tree rings, where if you have a thick ring, that indicates that there was a lot of growth that year. Well, bones don't grow like trees, so the process is a little more complicated, but it's the same basic idea. We can tell how fast an animal grew by looking at its bones. You need an actual fossil for this. You can't do this from a model, but if you do chemistry and physics to it, you can figure out what the animal's body temperature was during life. So you can tell how much energy it was having to take in to maintain its body temperature. Because of geology, we know how hot the world was. We know that if an organism is growing, it's taking in more energy than it strictly needs just to stay alive. You already knew this because you know that if a kid doesn't eat enough, they will have stunted growth. Eat your vegetables, stay away from cigarettes. And based on how much space it had in here for its belly and its guts, we can figure out how much food it could hold. So we know how often it would have to fill its belly in order to maintain that energy level. We figure it was about 2 to 3 weeks. But we have fossilized dinosaur poop. I'm not sure that this is actually from a dinosaur. This definitely isn't from a Tyrannosaurus, but this is an example of a Coprolite. And when we cut open fossilized dinosaur poop, we can see what they were eating. And when we cut open Tyrannosaurus poop, we find bits of bone. And bone is really hard to digest. It has to be in the stomach for a long time. So that tells us that the Tyrannosaurus was eating pretty frequently, that it was able to, not hold its food for long enough for the bone to digest. What can we infer about this 8-ton animal's habitat that it was taking all of this energy from? We don't have 8-ton two-legged animals walking around today. Does that mean this animal was adapted for an environment that doesn't exist anymore? For example, when I look at this guy, I think it's pretty reasonable to say that he couldn't fly. He doesn't have the build that I would expect if he were living out in the open ocean, like a whale, so that means he was a land animal. Well, what land habitat would he be suited to? In general, an animal this big, making its living the way it did, would have needed a lot of space and a lot of plants and animals around. Early on, paleontologists didn't know what modern animals they could compare Tyrannosaurus to. We just don't have that many large two-legged animals walking around. The thing they settled on was either it was walking like a human with its tail dragging on the ground, this is why Godzilla walks this way, or it was walking like a kangaroo. So let's do some science to this skeleton and see if it has the traits we would expect it to have if it were walking like Godzilla or like a kangaroo. Well, when kangaroos are just standing, they use their whole foot. That's sort of like how we stand. So we would expect to see a heel and a sort of mammal-like foot in front of it. Instead, we see really long, three-toed, bird-like foot. It even has a dew claw, so we know that that wasn't for walking on. It was walking just on its toes, like a large ground bird. There are other dinosaurs that walked just on the very tips of their toes, like a cow or a horse does today. But they had pretty short, stubby toes with long feet, whereas this guy has these really long, springy toes with huge claws. What does that say about the way he moved? What advantage did it give him to have these long, springy toes to push himself forward with? If this guy were dragging his tail or even standing on it like a kangaroo, he would be using it as another foot. So you would expect to see a lot of up and down flexibility, and you would see that these dangly parts on the bottom, which are called chevrons, would end about halfway down the tail like they do in kangaroos. They don't. They go all the way down to the tip, which tells us that it would have been holding its tail off the ground. We also know that it wasn't really very flexible. It could move, but it wasn't rat-like because it had these tall spines on top, which would have anchored muscles to be able to hold it aloft. So if it's going to be difficult for him to put his weight on it, and if it's going to be relatively easy for him to hold it off the ground, what does that tell us he was using it for? Another thing we would expect to see if this was moving like a kangaroo is much longer forelimbs. Kangaroos don't actually walk on 2 legs a lot of the time. They'll sort of alternate between using their tail and their front legs and then their back legs. Tyrannosaurus could not have done that. There were dinosaurs that could optionally walk on their front legs, but they would have a really long hand bones and short finger bones, whereas Tyrannosaurus has long finger bones and long claws. It also couldn't rotate its hand to face downwards towards the ground. This is something we only recently figured out, is that a lot of dinosaurs, Tyrannosaurus included, couldn't do this. So we've deduced that a kangaroo is not a good modern animal to compare this guy to, but a modern ground bird is. Now, when we look at a modern ground bird, we see this sort of suspension system in their thighs that helps them walk and balance easily. This guy is way bigger than any ground bird and has a longer tail, but I think he has something like that going on. Here we are at the hip. Now that we have a decent idea of what animals we're trying to compare this to, I can say that yes, this is a pretty bird-like hip. At least the top and the back of it are, and the thigh bones basically look like drumsticks. So I'm going to say that it is totally supported by the evidence of the skeleton that it would have had a bird-like balancing system for its hips and its thighs. That's actually why we have this dowel in the front of the animal holding it up, because we didn't want to have it standing on its tail because that's inaccurate. But it doesn't have the muscles and ligaments and tendons that would help it balance just on its legs. So we had to give it a crutch. While the top of the hip might look bird-like, when we look at the groin bone, it's indicating that it's a lizard-hipped dinosaur. This is actually pretty interesting because, like all dinosaurs, the way that the hip bones and the spine fit together says that the legs would be pointing downwards and supporting the creature from underneath, as opposed to with a lizard, you would have the legs sprawling outward. This is one of the main advantages that dinosaurs had when they first showed up. So what does that say about an adaptation that it's basically unchanged for 150 million years? These spines poking out from either side of the tail and ending about halfway down it, and this little bit that pokes out on the back of the thigh bone, tell us that, similar to what a crocodile has, it had a series of muscles running from its tail to its thigh bone. That gives it a really powerful set of muscles to push itself forward. So when I look at those absurdly muscular legs, which are pretty long compared to his body for a dinosaur, and I see just the general athletic build of the guy, I want to say that he is probably faster than other animals in his ecosystem that are his size. Now, why does he have these really long butt bones and really long forward-pointing groin bones with these huge boots on them? What purpose could he have for expending all of that energy growing these? Well, we know that with dinosaurs and other animals related to them, they actually have a muscle that runs from these dangly bits back here underneath the hip bones and pulls down here underneath the lungs. Think about when you are running or otherwise exerting yourself, and think about how you have to breathe separately from whatever it is your limbs are doing. Not so with this guy. He could actually automatically pull air into and push air out of his lungs and air sac system just using the mechanism of walking. By exaggerating that adaptation, what might not he need elsewhere? For instance, I don't see the big, deep, boxy ribcage that you see on some of the duck-billed dinosaurs or other bird-hipped dinosaurs that existed in his ecosystem. Maybe because he had such an efficient means for pumping air through his system, he didn't need a lot of capacity. We usually talk about competition for resources happening between animals, like separate individuals. But there's also competition for resources within an animal because it takes energy to grow, which means the most important adaptations for the role that the creature plays in its ecosystem are the ones that are going to get the lion's share of resources. So when you see something that might at first seem somewhat useless, like say for example his arms, maybe don't ask, well, what in the world did he use them for? Instead ask, what did he need more than those? So adaptation is sometimes a bit like skill points in a video game. You can't be good at everything at once. We need to ask, what didn't this guy need to do, just as much as we ask, what could he do really well? I mention this now because with regards to his arms, it's usually kind of a joke with T-Rex. There's a lot of stuff, especially on the internet, that it would be hilariously inept at things that humans use our arms for. So we have to ask, what did he need more than that ability? Well, I see this big, thick, probably really muscular neck, and I see this enormous head, maybe he just couldn't support bigger, heavier arms because then he would fall over forwards, or have to have an absurdly long tail, and then maybe he's too heavy to move. So think about, how was this guy getting energy from his environment that he needed brute force and not careful grasping? When we see these neck ribs with these long spines on the end, these are actually a way for him to have strong but jerky neck muscles without them taking up a bunch of space. So that goes into what we were saying earlier about moving a lot of air because he has a big windpipe, but that also means that he has a lot of room for a throat. That means that he needed a big throat. Now, what would he be consuming that requires a lot of space for the swallowing of things? When paleontologists first found T-Rex, they didn't have the whole skull, so they filled in the rest with what they knew about other large dinosaurs like this, which is what good paleontologists do. The weird thing is, we still see that skull on reproductions like our little museum replica, whereas actual Tyrannosaurus skull was pretty different from a lot of similar otherwise dinosaurs. When we look at this guy's mouth and teeth, you can pretty much determine just from those what he was doing for energy. These are not the grinding teeth in back and snipping tool in front teeth of a hadrosaur or other similar plant eater. These are not the simple pegs for raking foliage off of plants that a long-necked dinosaur would have. These teeth are shaped like pointy blades. He has an impressively large jawbone with these large ridges to attach muscles going up to the top of his head. So that tells us that he had a lot of force to close his mouth with. And when we put all of that together with our observation that this head is long and narrow in front and big and wide in back, we can infer what it might have been swallowing. I mentioned earlier that we have fossilized T-Rex poop with bone in it. Would we observe that and these adaptations if this were nibbling at a carcass and being picky about what it swallowed? Or is this going to crunch its prey to pulp and swallow it, bones and all? You will also notice that his eyes face mostly forward. You can tell because of the position of his eye sockets. Think about what animals today have eyes that face forward, as opposed to animals that have eyes that face in different directions, and why each has the arrangement that they do. What advantage does having your eyes work together have, and what advantage does having your eyes work separately have? And which role would this guy be fulfilling that he needed them to work together? We know, based on the rock that we find them in, that T-Rex lived at the very end of the age of dinosaurs, 68 to 66 million years ago. This animal's environment changed catastrophically. The environment the predators were adapted to, the environment the prey was adapted to, and that the prey's food, the plants, was adapted to, burned up when an asteroid smacked into the Gulf of Mexico. So remember that just because he's the biggest, strongest animal in his ecosystem doesn't mean that he's indestructible. We know that once his ecosystem couldn't support any herbivores bigger than a cat, he disappeared too. Look at this head and this powerful neck and these legs built for running and these enormous teeth, and imagine this creature hunting field mice. It's not what he's designed for. So when you're putting your model together today, please keep in mind, when we compare fossil organisms to other organisms in their habitat, as well as to modern organisms that either have a similar way of life or are related to them, we have to think carefully about what we see and what we don't see when we're trying to piece together how a fossil organism was adapted to its environment. We can also look at fossils to better understand the changes that led to the adaptations we see in modern organisms. When its ecosystem changes, an organism either moves, adapts, or dies out. The fossil record shows us examples of that happening. Sometimes, as with the non-bird dinosaurs, environment changes too quickly to adapt to, and across too large an area to move away from. Hopefully, you have a good idea of what you're going to look for in this model, and what you learn from those inquiries should be pretty useful when you're thinking about adaptations generally. I am Steven, this is the Geek Group, this is a Tyrannosaurus. Thank you for watching.
This video was made possible by a grant from the Future Girl Foundation.
This video was made possible by thousands of private donations from members and viewers like you. Please visit thegeekgroup.org for more information on how you can donate and become a part of our dreams of Avalon.